What Alex didn't mention in that lovely story about that 911 Targa is that it's actually just sitting in my garage right now, and he dumped it on me about a year ago.
Whoa, hold on a second.
That's because another part of the mobility problem is that parking in New York City is expensive, $650 a month. But if one has a friend in Arizona where the temperatures are optimal for storage of a vintage Porsche, there you go.
I'll be sending you an invoice, so thank you. Well, thank you again, and there's a lot to cover here, but before we get into anything, I think it's important because there's a lot of misunderstanding, because there's a lot of people out there who think that their Teslas are self-driving, and they're not. Let's define what we're talking about when we talk about AVs. Who wants to actually put this out there? Aris, do you want to? Joachim, do you want to? What are we talking about when we're talking about autonomous vehicles?
So there are maybe three broadly encountered levels of autonomy out there that needs to be carefully distinguished. First one being is maybe a bit derogatory term, but pseudo-autonomy. These are driver assistance systems that give you the feel of autonomous driving, but does not transfer the structure, does not change the structure of liabilities. You're still responsible for what's going on in the drive. Above that, there is the narrower field of highway pilot and traffic jam pilot, which is what we refer to in the industry as conditional autonomy. Under very strict conditions, the structure of liabilities change. The vehicle is responsible to conduct the drive, and the driver is not required. And then comes the level 4 of it, which is full autonomy. Important to denote that level 4 is not the utopia of level 5, drive anywhere, anytime, everywhere, without interferences, but it's a very broad operation envelope, and the vehicle is in charge of being able to stop safely once the situation, once he's encountering an exception, but that's still level 4 full autonomy.
So do you all agree that we're all in agreement that that is the levels that we want to be talking about? So we're going to be talking about level 4, and just for anyone who doesn't know what that necessarily means, you're not expected to be able to take over from the vehicle at any moment, but that geofence or that area or this operational domain might be limited. So, and that can mean a lot of things. It can mean geographic, and it can also mean limiting the ability to allow it to make a left-hand turn, actually, or never in rain. So we're going to talk about the challenges to achieving that. And before we do that, a societal question for a bunch of engineers, which should be fun. Why should we be doing this? Why? Is it just an engineering challenge, or is there, what's the benefit of it? Because, as we were discussing a little bit earlier, you could achieve a number of safety improvements by just putting interlocks on seatbelts, right? So why pursue AVs? Who wants to take the big question of the room? Alex or Joachim?
Let me try.
Okay.
Because from a societal perspective, there's certainly what probably most people associate with smart mobility, that is mobility as a service, that is easing up congestion in urban areas, making a better utilization of the roads and linking public transport with private mobility needs of all kinds of modes of transportation, and that requires automation. So I believe AVs definitely have a place there. The other is that access to mobility on a global scale is still growing, and therefore I would say safe mobility is the other aspects that justify automation. And there is probably as well an extension of today's ADAS systems possible to further reduce fatalities, to further improve safety on the roads. And obviously, most of the accidents today are caused by drivers. So provided that the AV serves the purposes that would be necessary even to get a regulatory approval, it will definitely as well improve road safety.
Alex, do you agree with that, or is there another reason, or Dipti?
Yeah, I agree, and I'd like to expand a little bit on it, just to illustrate the magnitude what we are talking about, right? Like, in the U.S., 30,000 people every year die in car accidents, and 90% of these are really caused by drivers under influence. So, per definition, with full autonomy, they are completely avoidable. Of course, we want to get to zero fatalities, so there are other areas we're still working on in terms of passive safety and so on. But full autonomy can have a dramatic impact on the fatalities. But also many people nowadays, they don't have access to mobility, right? Because they're handicapped or they're children and so on. So by offering full autonomy, we can expand the access to mobility and help improving lives. But also because of traffic congestion, right? People, the pain point number one for people who drive cars is really sitting in traffic jams. So by solving that problem and taking the driving task away, first of all, we'll make everybody's life easier, more comfortable. But the maybe even bigger part is that it's really wasted time. Many people sit in traffic jams and just sit there and they don't do anything. And we can give these people their time back. And giving them the time back and allowing them to be productive during that time, will generally improve productivity of the society, which basically is a huge economic driver. At the end of the day, it's the main driver for economic growth is productivity growth. So it generally can change the society overall, and it will have a lot of secondary impacts. Like, for example, once your commute is not so painful anymore because you don't have to drive, because you can be entertained or you're productive. You might don't worry so much if you live 15 minutes away from your work or you live an hour away from your work. That basically means you can maybe also live outside of the highly dense urban areas. So you will have impacts on the real estate market and generally maybe on traffic density and so on. So full autonomy will change everybody's life. That's why I think it's a very good cause to push for that.
And filled with all sorts of challenges. And so from where I sit, I see kind of like three main big umbrella challenges to the commercial deployment of AVs. So we should be clear about that, not demos. Commercial deployments. It's sort of under the business umbrella, the regulatory umbrella, and the technical umbrella. And I'm just wondering, under the technical piece first, I mean, Dipti, from your perspective, from ARM's perspective, what's the big technical challenge that has yet to be solved, or are we there? I mean, we've done all the good work, we're ready?
We've got a ways to go.
Okay.
And this is in full autonomous, right? When we look at the world of full autonomous, what we see are several aspects. First of all, ARM, most of you may know what it is, some of you may not. We develop IP that goes into most of anything that you hold today in your iPhone and interact with. So we are processing IP. And what we're investing in is all the IP that's necessary, technical semiconductor processors that are necessary for you to be able to go to production, for my friend here to be able to go to production in an autonomous vehicle. And when we look at that is a combination of very complex heterogeneous workloads. There's CPUs, there's machine learning that's happening, there's image processing, there's graphic processing. And so you put all of that together. The complexity, the system complexity of putting that together is yet to be fully solved. Today what we have is a data center on wheels, to my friend here. What we have is a data center on wheels that needs extensive cooling engines. And to solve that, we've got to solve the power and cost aspect of what that thing looks like. In addition to that, the software, algorithmic, the problems that need to be solved are extensive as well. And so we've got the makings, the startings of what's necessary to solve that problem, but to truly get to something that is scalable, as an industry, we've got to come together and solve these problems as one and collaborate across the board. And ARM just announced a consortium to start to do that, which is ADCC. There's others, but it is the industry coming together to start to solve the scalability aspect of autonomous vehicles.
So there's clearly a complexity, there's a lot of moving parts, and if I think of all the different layers that are required in to deploy commercially, I think of the basic level of compute. Are we at a point right now where we have enough compute to be able to commercially deploy?
Sure. For sure. But the question is, so the technical problem of driving a vehicle autonomously with a computer filling the trunk is mostly solved. Okay, that's
Mostly.
No, it's solved. I think the key gap in that technology is proving that it's solved. That's a technology of itself. The validation technologies of building the confidence by all standards that this vehicle is eligible to go on the road. But the technology is already there if you don't care for costs and power consumption, etc., etc. And we do care. So coming from the world of driver assistance, where this entire ecosystem, this entire value proposition started to evolve, there is great care when it comes to power consumption and compute, and most importantly, talking to the scalability, the economical scalability problem of autonomous driving, we need to consider the geographic scaling. The problem of high definition maps being built and being cured on a high refresh rate in a way that supports this autonomous driving proposition anywhere. And one of Mobileye's important assets is, of course, the fact that we are playing in the arena of driver assistance. We're quite affluent for 2 decades now in that arena. That gives us the very tangible value of harvesting information to automatically cure maps, to build a geoscaling which is economically scalable, and the less tangible ones, which is validating the technology over billions of driven miles of driver assistance. And the validation technology and the validation gap, which is a technology, as I said, of itself, is something that we're also tackling from that affluence in driver assistance.
So I do want to get back to the mapping piece, but just to address the compute, and I want to get maybe Vallejo's perspective or Volkswagen's perspective on this as well, which is you mentioned a couple of interesting things, which is like you're almost there, but to me being there means that it is not taking up your entire trunk, that you don't have major cooling issues, and then it's affordable. And so reframing that question to meeting those metrics, because that to me is what needs to happen to be able to do commercial deployment, right?
I'll respond shortly to that point.
Okay, and then I want to hear from these
yes, of course.
guys too.
So today in Mobileye's autonomous driving system, the self-driving system, we are relying on several IQ5 chips, period. Something that is far from a trunk full of compute. We see a roadmap to have two chips, IQ6, that's 6th generation, will support autonomous driving, robotaxi setup using 2 system on chips. So technology is already there in terms of compute.
So for Vallejo and also Volkswagen, I wonder, what's your opinion on that? Would you agree, or is there more to go?
Agreement depends a bit on this object as such, because I think in the last minutes we've been blurring 2 things which I tend to keep separate. The one being robotaxis, where it essentially is mobility as a service. It's providing a service which takes care as well in the SAE levels, very clearly puts that into an L4 bracket. So we're not talking L3 or anything below, and we're not talking about I think you called it utopia earlier, of level 5, where it would have to work absolutely anywhere under all conditions and so on, which I believe is a problem that's not solved. But the L4 challenge is solvable, or we are very close to having it solved as a service. Because a service is something that you choose to provide and you can basically revoke. You were talking earlier about the left turn, because you manage where the car is going, so you direct it around where there are no left turns. You make sure that you're driving only where you have sufficiently, let's say, high confidence in the accuracy of the map, and so on. And that's, I believe, therefore, the first step. And we probably can as well relax a bit the definition and say, is it a taxi that you hail? Is this device transporting other things than people off-peak and so on, which opens a vast opportunity in terms of automated logistics, but it's all in the service area. Now, to benefit from let's say, the free time in a traffic jam, etc., it brings us back to private ownership of vehicles, where we have no control what people might be doing with those vehicles wherever in the world they use them. And I think that brings us back to your original definition of conditional automation. So we can provide automation as well, I'm sure, at an affordable cost, but then it's going to be limited in space, in time, in use cases. And I think we need to keep those two apart: mobility as a service and private ownership.
So first of all, I think we have to differentiate between what we think we know how to solve and what is really solved.
Okay, so tell us what you've solved.
So let me first get it. I'd like to describe it a bit more. So first of all, the full autonomy system is an extremely complex system, and the high performance compute is one piece of it. So I think we probably know how to solve the high performance compute piece. So there's a technology to improve the efficiency, so the power versus compute performance ratios onto levels where it becomes acceptable, and there's a roadmap to bring the cost down. But it's not done yet, right? We haven't actually solved it, but I think we know how to solve it. But however, because that system is so complex, and the system consists of many pieces which are interdependent, so the sensor constellation, what type of sensor modalities we use, how many sensors, what field of use, what overlap and redundancies, and the compute, the sensor constellation then defines the requirements for the compute and the requirements for the algorithms. So all these pieces are interdependent, and they all have a huge latency, so inertia, which basically means once you know what the requirements are, it takes you years to actually get the real hardware. And that really makes that problem so tough. It's a huge system optimization problem with many different factors which influence each other.
And a supply chain problem too, then?
Of course, because the supply chain is part of it. Once you know how the requirements for your compute are, it takes you years to actually get the real hardware, right? So that's why I'm saying it's one thing to say we know how to solve it, and the other thing is that we have solved it and we actually have the hardware at hand. So I think even in this space, there's still a lot of work to be done, and we have just talked a little bit about this early on.
Yeah, and to expand on what we talked about earlier, now talk about security and cybersecurity. You and I, and then the interdependency of the security of this thing that now is a missile on the road that can be taken over, and how that implication has back to the compute. And so the world I live in, we live in a world where we're creating IP that eventually goes into compute, that eventually goes into silicon, that eventually somebody writes software on. And so we're way ahead of that supply chain, per se, of problem solving. And we're thinking about, well, gosh, if we've got to have this safety that's going to be innate in the processing, it's got to be innate in the computing. Safety is several aspects of safety, and it starts with the compute. Then you also have security. What is the implications of the system level security back down to the compute? And so again, to the question of, is it solved, or do we know how to solve it? We're at various aspects of that.
where are we on the cybersecurity piece of it? Because there's a lot of layers of security that need to occur within an AV, all the way down to the most basic components, the building blocks of the vehicle. So it certainly is a challenge, but how have we solved that cybersecurity issue, and what are the weak points? Is it in that supply chain that we don't exactly know the level of security in each piece, or is there something else?
How come you say we have solved it?
I don't know. Have we solved it?
I don't think we have even started solving it. Okay, so again, it's a bit of a broad topic, but basically we're just at the point where cars are getting the level of connectivity where they start to be really exposed to outside attacks, and therefore there are a few examples, but it's not representative yet of what is to come. And to solve the topic is probably partially linked, as you said, to compute power, but it's as well linked to system design and the way of the entire hardware and software architecture of the vehicle. And those are about to change drastically. I believe there is a general agreement that the way it used to be built in the past, like you add bits and pieces here or there, is not, let's say, the sustainable solution for the future. Therefore, an electronic architecture that takes into account the resilience that you would need in order to detect intrusion, to isolate and partially turn off activities in a fail-silent operation. I guess, in principle, again, we know how to do it, but we've not done it yet. And this will only come to fruition a few years down the road when these vehicles with those new architectures come on the road.
So a few times today, I've heard this roadmap. Like, we see the roadmap for compute, we see the roadmap for the systems, but then of course it's building it, putting it all together, and then deploying it. And so then it becomes a question of timelines. You know, is it an issue? Is one of the big pinch points on just the supply chain level, and that it just takes a while, and that we should just be more patient with it? Or is there something I'm missing here, that there is a different hindrance that's potentially slowing this timeline down to get to that level you were talking about, and to get to the level that Alex was talking about in terms of vehicle architecture and the entire system?
Maybe a very quick response, because I was just making that comment earlier. I see it as a normal, like, push and pull situation, where what we are going through now regarding cybersecurity, which is the topic you raised, is, from my point of view, similar to what we did with functional safety or whatever in the past. So there are processes being deployed that are developed in parallel to the product development. We're not having masses of AVs on the road tomorrow. But by the time these AVs will be there, the cybersecurity and other processes will have matured to the necessary level. I'm fully confident of that.
Just to add a little bit on that, because I think cybersecurity sort of traditionally has often been a bit of an afterthought. So you have an architecture and then you solve the cybersecurity problem later on. I think the requirements for cybersecurity for a fully autonomous vehicle will just skyrocket because in a vehicle where you have a human driving, and even if you hack the vehicle, you have a human safety layer in there who can take over the vehicle and stop the vehicle and so on. Right? Once you don't have the driver anymore, you basically have a missile. Somebody can control. It's the requirements will skyrocket. So, and real cybersecurity, I think you can only achieve on the architecture level. So first, you have to have a very good understanding of how to make a system extremely robust, what architecture requirements and drive, and then architect your complete system around. And it goes right down to the very bottom of the foundation of the system, starting with operating system and starting with compute architecture. So it's right from an afterthought becoming the first thing you need to think about when you architect a system. So that's why I think it is one of the absolute key topics which have not been talked about that much.
The architecture piece, or
The cybersecurity requirements which drive architecture.
I want to comment. I think I'm hearing your sentiment of like a top-down, from scratch system development, which is far from being the case. As I started saying earlier, which is very important to look at the fact that autonomous driving functionality is a growth which is organic to the driver assistance ecosystem. It's not from scratch. As Joachim mentioned, we already tackled challenges of functional safety when we come to consumer driver assistance. Cybersecurity is important even if all you have is an emergency braking system. It's already been tackled, so it's completely tackled for the case of robotaxi, but it doesn't mean let's wipe off the whiteboard and start from scratch. And that's where this moonshot from scratch perspective, we should be very careful with it, because the reality of robotaxi as an organic step from driver assistance system is much closer than what some of the sentiments made around cybersecurity or re-architecture have been made here. This is why we can more solidly move forward, fastly move forward, because we have built confidence in architectural questions, perception questions, control questions, safety questions in the course of driver assistance development. I do see that, of course, it's not a insignificant step forward, and we are all working to validate that step, but it's not a from scratch, let's redesign everything and come up with it.
I want to, I don't know if Alex or Dipti want to respond to that. I'm curious if you would agree to that, because it seems like there maybe is a difference on whether it should be for scratch or by scratch, or this sort of progression is the way I understand it.
So the development itself, it's an iterative process, right? We're not working on full autonomy somewhere locked away and one day will turn up and everything is done. So it's an iterative process where you upgrade your systems, you upgrade your software, you upgrade your hardware on a regular basis. But the point is that it's one thing to be able to go out and drive with a safety driver and basically be in a pilot phase. That's one thing. The other thing is to be able to sell vehicles to millions of or hundreds of thousands, millions of people, and really have a very robust automotive grade product. And so these are two different things. And in order to be able to do that, the automotive industry is good in that, but that takes time, and it has to sort of include it has to start really from an architectural point of view, and so you have to have these problems in mind when you architect the system, and whenever you try to make it as an afterthought, you will end up with a compromise. And the system is too complex in order to take compromises. So it's a very complex problem, which, like I said, in my view, can only solved when you have the right inputs already during the architecture stage.
And I think you're saying the same thing in that it is an iterative process, which means we build on what we have today. And as we learn through the execution and the deployment of, we then apply. But in addition to that, if you look at our world of, I'll go back to safety, since we're saying we've solved the safety problem. If you look at our world of safety, your standards are ASLB and ASLD safety, and then those were designed in a world for a driver vehicle, not even designed for some of the complexities of ADAS that are there. So we're in the process of revisiting, are those safety standards still the right ones when we look at fully autonomous vehicles? And so do you call that an iterative process? Somewhat. We learned through those deployments, through having deployments of ASLB and ASLD, and we say, gosh, that's not going to be enough for what we truly need. And those standards don't scale completely today. So yes, we've solved it, but we've got to continue evolving, right?
Question, a note on that. Thanks for that point. The functional safety versus nominal safety is a key item of discussion. I just want to exemplify to give a quick reference. Even in driver assistance systems, there are safety goals with immense gravity. If you drive on a lane-centering vehicle, a vehicle that promises you that it will maintain lane, and that vehicle drives into the concrete barrier, that's a high gravity problem. Okay, that's a very concrete problem, if to be no pun intended. So the ability to protect those safety goals in the world of driver assistance is the same practice that's going to allow us to protect these safety goals in a robotaxi setup. Again, a continuum, not we're doing something completely new. That's the idea.
And I believe that's a key point here, that it's not a competition of this is better than this, or this was not good, so put it aside and start from scratch. You need to build on what we have, and basically when you refer to ASIL, that's the automotive adaptation or extension of the safety integrity levels that have been around for decades for nuclear power plants or whatever you name it, and I believe also there when it comes to AVs in general, maybe cybersecurity in particular, there are lots of examples we can take from other industries. We should not be blind and say, well, that's not in the car. We have standards that we can build on. We have experience that has been gained elsewhere that we need to transfer. And as such, probably the process will never stop. You said it's iterative. It's a never-ending process, because whatever solutions we find, somebody will find poke a hole in them somewhere, and the challenge will be to be able to respond quickly and to make sure that whatever intrusion might happen does not lead to, well, fatal consequences, and that's coming back then to the overall architecture of the system. So I think there is no disagreement there.
Right. Well, I would say iteration is important. Of course, if your foundation is fundamentally flawed, then you do have to potentially start over from scratch, and you don't know that until sometimes you're pretty far down the road.
And when we look at, to your point of iteration, when we look at this autonomous, in my role, I run both IoT and automotive. There are a lot of analogies that you can take from securing robots inside of factories and things of that sort, the base technology, the base compute, the base safety. So yes, we're learning from other industries just the same. We learn from whatever standards have been there previously in automotive and also other industries and how those deployments have worked. And if you look at factories, we've figured out ways to scale, right? From the base levels to really complex problems and from a hardware and software point of view. And I think we'll see a similar analogy play out in autonomous as well.
There's like 3 other layers of the vehicle in an AV that I want to address, and we're pretty short on time. So I do want to just quickly address sensors. In terms of radar, LiDAR, and vision, are we there? Is there a startup somewhere maybe out in the exhibit hall that's going to come up with something better? I mean, technically speaking, has that been achieved? And I understand that, except for maybe Elon Musk and Anthony Lewandowski, who believe that LiDAR is a crutch, the rest of the industry believes that they need to be combined. So it's a twofold question. Are we there yet? And how much farther do we have to go? And then can it be achieved without, let's say, LiDAR that could be a full vision system at some point? And I'll give it to Mobileye, since that's sort of your expertise.
Sure. So most definitely, and I think it's been just reinforced and reestablished that the solution for that vehicle to be as expressive in its decision as it needs to be, to have a comprehensive grasp of what's going on around him, which is the road boundaries, road users, road geometry, and road semantics. These are the 4 pillars of what is the environment. And it's been established that visual perception is still the core foundation that allows you to get a comprehensive, robust, and actionable understanding of the environment. For matters of redundancies, to make sure that your failure rate is bound, that you can prove that your failure rate is bound. Even, again, the technology of proving things is a technology by itself. there comes the redundancies. And I do, to your second question, I do believe that in today's span of solutions available, a LiDAR as part of that redundancy is needed. Although the field of high angular resolution radars, as it moves forward, might change that equation, but as of now, I believe all three components are in the game.
So do you want to weigh in really quickly?
Yeah, just to add, I think because it's one of the sort of success stories, I think huge advances have been made on perception, and probably because this has been seen as the biggest problem, and so a lot of research and a lot of work has went into that, and so the industry has made massive progress. And also to come back to your sensors, has this been solved and so on. Also there are a lot of the very promising technology steps in the pipeline to solve really the sensor problem, and to be able to bring the sensor costs down and be able to scale these up. And obviously Mobileye has also participated to a large extent to that.
We're out of time, but I do have one question. It's the easiest one, so don't worry. As briefly as you can, identify what the biggest threat is to autonomous vehicles, each one of you. What could derail AVs? What's the biggest threat? It's an easy one. You'll be fine.
Sure, it is. So I think on top of the functional safety that we just described, which is how do you guarantee that the vehicle is doing what it was designed to do, we need what the vehicle is designed to do would be the correct thing, and that's the nominal safety, the decision-making of the vehicle, and building the confidence that those vehicles' decision-making framework is safe in a way that the human can perceive it as safe. It's corresponding with society about the safety of the solution, through regulators or to the consumers.
There's not really much to add. That was a very comprehensive one. but maybe very much down to earth. I believe we all have to take great care about safety, because you said earlier, how do we get people on those vehicles? And if people lose confidence in the safety of driverless mobility, all the technical solutions serve no purpose. So that's the key challenge that we have to meet in designing and releasing those vehicles on the road.
Right, because something could, a fatality in an AV testing could derail a number of programs. We've already kind of seen that happen at least once. So.
Yeah, and I think I would agree with what's been said already, which is it's the human. We're dealing with human beings, which are very complex, and decision makings and perception isn't always reality, and vice versa. I think we are not going to be as forgiving to a vehicle in an accident as we are. We are absolutely not going to be as forgiving to a vehicle in an accident, an autonomous vehicle, versus a human being. We have accidents every day, and we accept them. But when that happens on an autonomous vehicle, that'll be front page news.
Yeah, these were all very great arguments. So it's not. I mean, I would have said the same things. I would just maybe add one more. And this is because it's such a difficult problem, and it requires so much investment. So we depend on the willingness of large companies to make these investments. And for every company, there needs to be a business case behind this. So if it is the problem maybe even harder than we think, and it will take even longer than we think, and maybe the economic environment, the macro environment will get more difficult. Maybe these investments will slow down, and that could drag out the whole system and so on, the whole process. So I think that's not to underestimate as well.
Well, we could address a number of other challenges too. I would say, like, just convincing people to get into the vehicle, even if it works perfectly, is another piece of it. So people, money, safety, and what? And geography. Okay, great. Well, thanks so much, and hanging in there with us while we went a little bit over, but I'm glad we did. All right, thank you.